I have here a container of red and white beads. I'm not sure what proportion of beads in the container are red. Hopefully I wrote it down somewhere, but I'm going to take a sample from this population. So this population has some proportion P equal to the percentage of red beads in this container. Now I've got this little paddle here that allows me to take a sample. And the sample of 20 has 1, 2, 3, 4, 5, 6, 7, 8 red beads in it. So 8 out of 20 then would be a sample of 40% red. So my sample statistic P hat is 0.4. If I dump out that sample, that's not good. I dropped some beads. I got to find my little beads here. If I dump out this, if I take another sample from the same population, now I have 1, 2, 3, 4, 5, 6, 7. I got 40% again. Take a third sample. 1, 2, 3, 4, 5. This is crazy. I keep eating the same sample proportion each time. Samples are supposed to vary, but I'm having, so let me do another sample. 1, 2, 3, 4, 5, 6. This time I have a 30 or 6 out of 20 red beads. Why am I having so much trouble? That'd be 30%. So actually the 7 out of 20 would be 35%, not 40%. So if I were to take multiple samples here from the same population, so fill in all my little slots, 1, 2, 3, 4, 5, 6, 7, 8, this time would be 40%. So I can get different sample proportions from the same population that has the same proportion. Now we've done this a lot in the past, and this is called a sampling distribution. We're going to talk about a sampling distribution in just a minute, but I want to show an example here that maybe shows what I'm doing in another way. So I'm going to change this to green and white beads. I think in the handout it says green and red and green, but I'm going to change it to red and white to match what we did. And let's just say I have 100 red beads and 100 white beads in a container. And I want to draw a sample of 20 beads, just like I did from my little jar of beads there, a little box of beads. And I want to calculate the sample proportion. So I have here a little screen, and if I push one run, it pops out. 8 out of my beads are red. So it drops at 40%. I have one sample of beads in which the proportion of red beads was 40. So I do another run. I get another 20 beads. This time 10 out of the 20 are red. So it drops a sample proportion here of where the proportion of red beads is 50. This time I have 11. So this is one where the sample of red beads is 55%. So I have 3 different sample proportions from the same population proportion. So we're going to fill in some information then on our notes about this. I start with the distribution of red and white beads in which 50% are red and 50% are white. So here's my red beads, here's my white beads. My population proportion of red beads is 0.5. So the distribution shows 50% red, 50% white. The first sample I got had 8 red and 12 white. So I had a population where 40% were red and 60% were white. So the distribution of my first sample would look like this, red and white. My second sample had 50% red and 50% white, just like the population. So my second sample looked like this, red and white. P hat in this case, which is the population or the sample proportion, was 8 over 20 or 0.4. Here P hat was 10 over 20, which is 0.5. My third sample had 11 red and 9 white. So it was a 0.55 and a 0.45. So 0.55 red, 0.45 white. So this is the distribution of my third sample. P hat here was 11 over 20 or 0.55. Now when I got the 3 sample statistics, I created what's called a sampling distribution. So I plotted one of my bars right here at 0.4. This is my first p hat. Then I plotted another bar at 0.5. That's my second p hat. So this is p hat number 1. This was p hat number 2. And then my third one was at 0.5 hat. That was p hat number 3. Now if I continue this process, I'm going to see what happens in the long run when I do lots and lots of samples of size 20 from the same population. So this distribution, these distributions here all consist of individual beads. Okay, these all have individual beads and how many of red and how many of white. But this distribution isn't a distribution of individual beads. This is a distribution of sample statistics. So each one of these are sample statistics. This is known as a sampling distribution of p hat. So let's go back and see what happens if we take lots and lots of these. So I have 3 right now. I'm going to get 1,000. Notice what happens in the long run here. I'm going to keep going and get another 1,000 and another 1,000 and another 1,000 and another 1,000, 5,000 altogether. Notice the distribution looks very unimodal and symmetric, very similar to a normal model. Notice that it looks like the smallest proportion I only got 4 of those. I got 15% red balls 4 times out of about 5,000, and I got 85 about 4 times out of 1,000. So the overall sampling distribution looks like this. This is a distribution of sample proportions from 5,003 different samples. So if we go back to the notes, this is known as a sampling distribution for p hat. The sampling distribution for p hat is defined as follows: the distribution of sample proportions for all possible samples of the same size, in this case n equals 20, from the same population. Now, when I did 5,003 samples in my little example just now, I didn't get all possible samples. I only got 5,003 samples. So this would technically be only an approximate sampling distribution, but we can be fairly certain that the real sampling distribution, including all possible samples, would look very, very much like what we have with 5,000 samples. So here was my distribution, kind of in a rough sketch. It was centered at 0.5. I'm going to go back and look at that. So we notice it's centered at 0.5, which is the true population proportion. It's actually centered slightly less than 0.5, but very, very close, 0.50006, okay, or maybe just 2 O's. It went from 0.15 to 0.85, very small, and it was really shaped a little bit more steeply here, but this is the best I could do in my space. We could describe it as being unimodal and symmetric, centered at 5 with a minimum of 0.15 and a maximum of 0.85. This is known as the sampling distribution for p hat. Each individual in this distribution is not an individual bead, it is an individual p hat. So these are all p hats. Lots and lots of p hats stacked on top of each other. That's what we have. Now, I have a question for you. Mrs. Taylor pulls a random sample of 20 beads from a container of red and white beads that she claims is 50% red. 17 of the 20 beads are red. What do you conclude about Mrs. Taylor's claim? Explain your reasoning. Okay, well, I'm going to go back and look and see. If I pulled 17 out of 20, that would be 85%. So I look here. I only had 3 times out of 5,003 samples. I'm going to do another 1,000, see if it makes any difference at all. Okay, 4 this time. 4 out of 6,003 that were 85%. That's an extremely small number. So if Mrs. Taylor pulled 17 out of 20 out of a bead basket of beads, I would suspect the proportion of red beads in that container is really not 50%. It's really more than 50%, because it would be so very unusual to get a sample like that from a population where their red beads were 50%. So in writing this, I could say that a sample proportion of 85% is possible, but very unlikely. Now, this was a previous example I used, not the one I just showed you, but it happened only 3 out of 6,006 times in my simulation. My simulation I just did now, it was 4 out of 6,003, but basically the same thing. Therefore, I have very strong doubts that p is really 0.5. So in statistics, we're actually really happy when something is unusually low. When there's a probability of unusually low of something happening, then we can actually make a decision. Then we can actually think, there is something I could say about this. I could say, I don't think it's 50%. Now, if I got a sample proportion, say, of 70%, somewhat unusual, but it could plausibly have come from a sample with a population, could have come from a population where the percentage of red beads was 50%. It maybe couldn't have, maybe it didn't, but we don't know for sure. It's not unusual enough to reject this claim. So here, though, this is so unusual, I really feel pretty strongly that I could reject this claim. So this is what we do with sampling distributions. With sampling distributions, we look to see what is likely to happen with a statistic and when a statistic is unusual or unlikely to happen from a certain population. So this gives us an idea of how much variability we can expect in our samples from a certain population.